Hey everyone, my name is Rubens, and I work with Fred and Kunle at Stanford, and I'll be talking about challenges of hardware-software co-design for Sparse ML and streaming Dataflow. So in recent years, there's been an explosion in ML models, all while the hardware has not been able to keep up, and nowadays massive amounts of compute power are needed to train and run large AI models. This trend has shown that AI is now a supercomputing problem, so now having more efficient hardware is crucial to being able to keep up with that growth. To improve performance, Dataflow accelerators, as Paul has introduced before, has gained traction over the years, both fixed function and reconfigurable, and they provide better performance over traditional von Neumann architectures. And they're typically made up of a grid of compute and memory units, allowing the data to flow. To scale models, researchers have looked in depth into different methods, including decreasing model size through incorporating sparsity and quantization, or building more efficient hardware accelerators. And today I'll just be focusing more on sparsity and efficient hardware accelerators or ASICs. It's also worth noting that most accelerators today constrain users to adapt or change their models to fit their specific hardware. However, to be able to represent the large space of models and being able to adapt to algorithm changes over time, generality is key to for the next wave of Dataflow AI accelerators. And that is generality in data and sparsity, and generality in programming model, all while being able to provide good performance across the space. So why do we need generality? This just shows that a lot of different models currently exist today, and there are a lot of new models being developed. Whether these are new flavors of transformer models or completely different models with different sets of features. And the question then becomes, how do you design the hardware such that it is adaptable to new models over time? To identify what we need, we looked into state-of-the-art compilation tools such as Fireworks Sparse Abstract Machine, or SAM, which provides a logical IR that can express all of tensor algebra on Dataflow hardware. It consists of composable primitives, all that are general enough to be composed to form any sets of tensor algebra expressions. For example, for sparse matrix multiply, you can use these sets of blocks that are provided in SAM to stream the entire application. We then explored these state-of-the-art models, transformers, and GNNs, and tried to port them onto SAM, the Sparse Abstract Machine, and found that there were several shortcomings when trying to do so. For example, for transformers, you have these tensor operations, tensor multiplication, tensor addition. However, there are these data movement operations and nonlinear operations and data generators that are currently not supported in SAM. Similarly, for GNNs, you have linear algebra operations, which are supported in SAM, whereas you don't have these similar operations that are not supported in SAM. So to establish a general ML Dataflow accelerator, we are building on top of Fireworks SAM and adding new components and features to be able to represent the large space of sparse ML models. And these will be the new contributions, including the Sparse ML Dataflow accelerator and a deep learning compiler to make efficient use of that accelerator. These are the key challenges that we run into when trying to design this accelerator. And this includes missing hardware features, data optimization, and sparse data patterns. The first key piece is missing hardware features. To achieve generality, we need more than just tensor algebra, as we've shown before when trying to explore different models. We need these data movement operations and nonlinear operations, all while minimizing communication and memory overhead. And we also need more composable hardware primitives that are general enough to be, so we can have just a few set of them to be generalized to form any operation that could be involved in a sparse ML model. We started off by adding these new hardware features, including for memory movement primitives, which were shown in the previous slide for sparse shape operators. We also added operations for nonlinear operations, and these include a filter block, which can be used for applying masking to a tensor. As an example shown on the right, you could just pass in a condition operator based on either the coordinates or the values to return the desired output. In this case, it's just a triangular lower for the input tensor. We also added unary LE for unary operations, which allows the user to element-wise operations over a stream of data. Although now we are able to implement end-to-end models using these new features, more hardware features still need to be added to keep up with future models. The second challenge we came across is data flow optimization, and this includes kernel fusion and data flow order. Deep learning models often consist of multiple layers, and being able to identify fusion opportunities across different layers is key to performance, and we need to be able to fuse when possible. And prior work deep learning compilers, such as TVM and XLA, typically focus more on dense fusion, which is different from sparse fusion, or algebraic fusion. Moreover, data flow is crucial to achieving good performance, and data flow just determines the order of iteration, order of computation. As shown on the right, we show the different data flows for sparse matrix multiply, and you can see the different access patterns based on the selected data flow, based on inner product, outer product, or row-based. And data flow order can make or break performance, as selecting the wrong order can lead to asymptotically worse performance. So we need something to be able to reason about the iteration order for each kernel to be able to get good performance for an end-to-end model. And moreover, the kernel fusion requires identical data flow order across all the different kernels to be fused. To tackle this challenge, we need a compiler for data flow optimization. Like we've learned from prior work in Taco and Sam, the compiler should generate fused code by default. As shown on the right, we benchmarked a standard attention module from the transformer application and show how just by fusing the different operations involving an attention module, we can get more than double the performance. However, in machine learning, fusion may not always be possible for correctness. So we need a language and compiler to be able to not only perform sparse kernel fusion, but also being able to detect when it is feasible to fuse and also when it is not possible to ensure correctness, and when to break fusion for these cases. Additionally, the compiler should determine the most performant data flow order. As we show on the right, we benchmark the first tensor multiplication in the attention module and show how just by varying data flow orders, the performance is drastically different. As mentioned before, kernel fusion requires identical data flow order across different kernels to be fused. So the compiler should be smart in reasoning about the trade-off between the iteration order for each kernel in a fused kernel. So for example, you could have a case where the selected iteration order is performant for one of the kernels and the stack of kernels to be fused. However, it performs worse on the other kernels. So you need to be able to optimize end-to-end rather than by kernel basis. So the language and compiler should be able to perform dynamic selection of iteration order, whether that is through online or offline methods. And also, the language should provide an input API usability for redundant layers, which are abundant in machine learning models. And this needs to incorporate a compiler transformation for automatic kernel fusion for these cases. To be general, we also need to worry about representing sparse data patterns. There are various sparsity patterns in ML. This could include unstructured block sparsity or diagonal structures. As shown on the right, we show the top shows a block sparse structure. The middle shows more advanced structure sparsity patterns, such as prior work in pixelated butterfly, which is an algorithm for ensuring a specific structured block format for different layers in ML. And it provides good performance in GPUs because of the dense blocks that are efficient to compute on GPUs. Prior work AI accelerators typically constrain users to specific sparsity patterns. For example, NVIDIA's A100 tensor cores, they guarantee great performance for their 2x4 structure sparsity, where they prove 2 elements out of every 4 row blocks. And these constraints limit the user in what kind of sparsity they could express on their models. To explore sparse data patterns, we need a language and data flow hardware support for representing the entire space of ML and not just a selected few for specific hardware such as the A100 tensor core. And the compiler should also be able to pick optimal formats for different structures, as well as being able to efficiently coiterate between different structures. And as shown on the right, we benchmark a different format for performing block sparse tensor multiply and show how just by storing it differently, we can get drastically better performance. Or in the unstructured case, we store one coordinate for each element in a dense block, whereas in the block case, we just store one coordinate for each block. And that allows us to use dense compute units such as systolic arrays to be able to compute those dense blocks over these dense blocks. We also need to embed sparse data pattern representation in the language to allow the user to represent any types of sparsity that they would like. In conclusion, we believe that generality is key for the next wave of AI accelerators Dataflow, and we show that AI accelerators and compilers need to incorporate ML-specific features, optimizations, and data patterns. And we need a language to be able to achieve those features. Thank you.